right, so today we're going to be talking about week 2, which is where we start to do stuff with matrices and kind of show how we can utilize them to solve certain types of problems and kind of gearing up to use it in different applications in some following weeks. So right now we're going to be doing 2.1, which is discussing systems of equations and something called Gaussian elimination. So we'll talk about that and what we're going to do. So, okay, 2.1, we're talking about how we can use matrices to represent systems of linear equations. So kind of with this example down here, I feel like it's the best way to understand it, is a linear equation is an equation where we have things being linearly combined. So by definition of linearly combined, we're only going to be multiplying things by numbers, so like scalars, and we will be using variables. So in this class, we usually use like x, y, z, or like x1, x2, x3. And so we can combine x, y, and z's, or x1s, x2, x3s with addition and subtraction. And then with some numbers. So like in this case, it's like 2 and 3 are our coefficients. And then the x and the y terms are being added. When the x and y terms are no longer being added together, instead they're like multiplied together, or like in week 9 when we get to differentials, so like derivatives, that is no longer a linear equation. That is, in week 9 is a differential equation, and then later on, like if you were multiplying x times y, that's not a linear equation, and you cannot use matrices to represent it, or this is the way that we talk about it in this class. So linear equations, again, is linear combinations. So we can represent systems of these. So we have multiple, which you're definitely familiar with systems of linear equations. You've probably done them in high school or in lower math classes, but we can use matrices to represent what these systems look like. So in this case, I can put each of these into a row in this system. So we'll be forming something of the form AX equals B. So A is going to be something called our coefficient matrix, which is where we put our coefficients. So like in example, 2, 3, -5, and -4 are our coefficients. They go in their corresponding spots in my coefficient matrix A. X is going to be a column vector. It's always going to be a column vector. And remember, column vectors are n by 1 matrices. So they only have multiple rows. They only have one column. So this is my column vector X. In this case, we use X to kind of describe if it's like X, Y, Z, or like X1, X2, X3, it doesn't really matter. Like the letter doesn't have to correspond exactly. And then B is going to be what our system is set equal to. So in this case, each of these equations are set equal to 5 and 8 respectively. So in our B vector, we're going to have 5 and 8. Let me get rid of all my writing. So we have A, X equals B. So A is an m by n matrix. This example has a square A matrix. It does not have to be square. And honestly, you're going to encounter a lot of situations where it's not square. So m by n, and then X is an n by 1. Note that these two things are the same. They must be the same. The idea of matrix multiplication carries through here. So these must be the same. So then the result is going to be an m by 1. So in this case, it's a 2 by 2 times a 2 by 1 gives us a 2 by 1. But again, it can be a 3 by 2 times a 2 by 1 to get us a 3 by 1. So just remember the rules about the sizes of things, how they must equal out. The middle term must be the same and the outside terms forms the product. So X is an n by 1 solution vector and B comes from the constant solution. When we're solving our systems of linear equations, we are solving for this value, this X. And then you can either have no solution. So when we have no solution, there's no possible way to make this be true. There's no combination of X's and Y's or X1s, X2s, X3s, etc., where this system can be true. It just is possible. An example of that I feel like would be like X plus Y equals 5, X plus Y equals 6. Something like this is one of those base examples, but there's no way for this to have a solution because it can't be true that X plus Y is 5 and X plus Y is 6. So no solution is one option. And then we can also have one solution. One solution is unique. So it's probably what you're more used to when you've been solving these systems, if you solve them like in lower levels of math classes, where there is a value for X and there's a value for Y, and that's the end of it. So I think like an example of that could be like X plus Y is 5, and then like Y is 6, like something like that. That obviously has one solution where y is 6 and then x is -1. That's the solution. That has one solution. -1 being x and then 6 being y is the only way for this system to be true. But we can have infinitely many solutions, which is probably the most common instance you'll see in this class, where we have multiple things that can be true for this. So I would say where x is equal to 2y. That should be infinitely many, I think. So I guess I'll rewrite this as x plus 2y is equal to 0. Yeah. X being equal to -2y and plugging that in, you can have a lot of different, actually, I don't know if this is true, but you get the idea. I'm really bad at coming up with examples off the top of my head, but where you have infinitely many things. So where multiple things can be true. And the way that we solve for this is we find what is kind of constructs the solutions that are of that form. Which ways can we change x and y in relationship to each other to make it fit into that system? That's what we're going to be solving for. So when you have no solution, that's kind of considered an inconsistent system. And then when you have one solution or infinitely many solutions, that is consistent because there is at least one solution. So these are only three options when it comes to solutions to ax equals b. We can either have no, one, or infinitely many solutions. So there's no like 2 solutions, 5 solutions. Also note that if we set b equal to 0, so this vector, if we say instead this is 0 and this is 0, this allows us to solve the homogeneous system ax equals 0. So ax equals b is the general solution, a general type of solution, and then within that we have a certain type of solutions within that idea. This is called the homogeneous solution. In this class, think homogeneous set equal to 0. If you remember that homogeneous means set equal to 0, you're in great shape. So in this case, when we solve x equals 0, that's a very specific type of solution that I will discuss in a bit, but very important concept. So we talked about systems of linear equations, and now we need to talk about what we do in this class kind of to solve these systems of linear equations using matrices. So that brings us the idea of Gaussian elimination. So the idea of it is Gaussian elimination is a process where we perform operations to the rows. So in this class, we do row operations. We do types of row operations. We switch to rows, we scale to rows, we do rows. Column operations exist, but don't do them. Just do row operations, move all the rows around, don't move the columns around. So we want to do these operations on rows to simplify the system and find a solution. So the point of this is kind of just to the way I like to think about it is we're getting to the crux of the system. What does it boil down to? You can have 1,000 rows of a system of linear equations, but you can eliminate 996 of them because they are redundant, right? We're only trying to get to what is exactly important about the specific system, what defines the relationship between the variables. So we'll use Gaussian elimination to solve. So there's something called echelon form. So echelon form is a form that of the matrix when it had row operations done to it, where the first entry in each row is a leading one. So with all these row operations, we can get it so that each row has a leading one. Essentially, it pretty much goes down to dividing each row by the value that it is in the first row. So if it's 5 to 6, if I just divide this first row by 5, I'm going to have 1 2/5, 6/5. That when every row, first entry in each row is a leading one, that's echelon form. However, in this class, we really want to get to something called reduced row echelon form, which the abbreviation is RREF. I will just refer to that as ref because I'm going to say it a lot in this class. But the reduced row echelon form is when the leading one in each row, so leading one means going from left to right, the first value, non-zero value in there. So in each row, the first entry is going to be a 1, just like with echelon form. But they're the only non-zero entry in their respective columns. So in this case, if I had Why did I write the same numbers again? 3, 3, 3, sure. Let me do all of these in this matrix echelon form. So like 1, 2, 6, 5, 6, 1, 1, 1. That has every leading one. The first entry in each row is a leading one. But my reduced row echelon form is where each of those leading ones are the first non-zero row, the first non-zero value, and every other entry in that column is a 0. So in this case, that would mean this is my leading one. There can be entries after it that are non-zero, but everything below it must be a 0. That would necessitate that instead, this would become our leading one in this row. So for that to be our leading one in this row, we'd have to multiply it by, what is that? 6, obviously, 6, 2, 6 over 2. So if I multiply this row, the second row, by 6 over 2, 2/5, 6 over 2, 6 over 2, 1, 2. 6 over 2 times 5, 6, 5, 2. Sorry, I realize that with fractions sometimes. 5, 2. So that would, I'm saying for the second row, if I change it so the second value is that leading one. However, remember, this can only be the only non-zero value in this column. So this must be a 0 and this must be a 0. Then this must be a 0. This must be a 0. It's a very powerful form. Yeah. If you can tell, it's going to take a little bit of effort to get matrices into reduced row echelon form because it requires that there's these leading ones in each row and their entire column is non-zero, is 0 besides that one value. So it takes a lot of effort, but it's going to simplify the system as much as possible. So once we get to reduced row echelon form, we know the system in its entirety. Let me get rid of all this yap. So we'll talk about how to solve for reduced row echelon form. Just know that that's what we're trying to get at. And the way that we get to reduced row echelon form is using these row operations. So I alluded to that before. There's 3 different types of row operations. There's type 1, where you switch 2 rows. So if I have row 1 and row 2, and I want to just switch row 1 and row 2. So I would do like row 1 is equal to row 1 is just equal to row 2. So that makes row 1 become row 2, and they switch. Type 2 is when you scale a row. That would be like row 1 is equal to 3 times row 1. So I want to multiply row 1 times 3. From what I was doing earlier, I was scaling the row because I was dividing by the value of that leading one. So dividing by 6 is the same as multiplying by 1/6. So think about it as multiplication by a fraction rather than dividing. And then type 3 is where you add a scaled row to another row. So for this case, it could be row 1 is equal to row 1 plus 3 row 2. So row 1 stays the same, but I add 3 times row 2. Seems a bit random, but it'll make sense why we would do that once we get to an example of reduced row echelon form. Here are some more definitions that are really important with the idea of systems of linear equations and stuff we'll talk about a lot in the future. So the kernel or the null space is the homogeneous solution. That is what we just talked about before. So I say homogeneous and homogeneous interchangeably. So this is when we solve AX equals 0. The kernel, the homogeneous, the null space, all of those words need to mean the same thing to you. Kernel, null space, homogeneous solution. Those are synonyms. Those mean the exact same thing. I don't know where the term kernel comes from. Null space makes sense because like null, I feel like means empty, which is where we're setting equal to 0. Null space makes sense. Homogeneous makes sense because homogeneous essentially means equal to 0 in all of math. Kernel, I don't know why it's called the kernel, but that's the term. Then we have the idea of pivot variables and free variables. So from when we talked about this system, the number of variables in your system of linear equations, obviously in this case is 2, but it's the number of columns. So the number of columns is equal to the number of variables, because let's look at here. So let's try to, I remove all of my writing on here. Let's go backwards. Let's see if we can go from here to here. So again, we're doing matrix multiplication. So we're doing row times column. I know we're setting this is a 2 by 2 and this is a 2 by 1. So I know my result is going to be a 2 by 1. So I'm gonna write the 2 by 1 up here, right like this. So it's always row times column. So row 2x plus 3y. Then it's row times column, negative 5x minus 4y, which gets us to what's here. So the number of columns in your coefficient matrix A tells you how many variables you have. So when we have these variables, they can either be pivot variables or free variables. Pivot, there's also a term, pivot means a basic variable. You might see it referred to either way in this class or in literature. So pivot equals a basic variable, and then a free variable is the opposite. So our number of pivot variables, so our pivot variables plus free variables is equal to our number of variables, which seems a little bit over-explanatory. But the idea is that a variable is only a pivot or a free variable, and they can't be both. So a pivot variable is a variable that's column has that leading one in the reduced for echelon form. So we have these leading ones, but we also can have columns that don't have those leading ones. We just know that a row must have that leading one, and then we can have columns that don't have that leading one corresponding to in it, if that makes sense. So the variables whose columns have that leading one, that's a pivot variable. And then a free variable is a variable whose value is dependent on the pivot variables. So the ones kind of define the system, the variables, and then the values of the free variables change based on the pivot variables. So again, these are all for, actually, let me pause for a second. Pivot variables, if your system, if you have one solution, you only have pivot variables. If you have infinitely many solutions, you have pivot and free variables. So the idea is when you have one solution, everything has a leading one and it is a pivot variable because it's just going to be a one-to-one correspondence with a variable and a value. When you have infinitely many solutions, you have those pivot variables, but then you have free variables because the point is that we have infinitely many solutions, that the solutions rely on each other. You can, if you set x equal to blah, 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 then y will be equal to blah, 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 and that will solve the system. So the free variables are the variables that change based on the values of the pivot variables. It'll make more sense once we do examples, but these are just definitions that you should have internalized, I guess. The rank is a number. So the rank is the number of non-zero rows in the reduced for echelon form. So when you have all of these rows where you have that leading one in each row, the number of rows with those leading ones, that is the rank. That is also, like it says, the number of pivot variables. It tells us a lot about the system. So if the rank is equal to the number of columns, we have some unique solutions, which occurs when we only have pivot variables, because in this expression, we have the pivot plus the free variables is the number of variables, which we also know is the number of columns. If we have, so following this, if the rank is equal to the number of columns, that means the rank tells us the number of pivot variables. That means that this value is equal to this value, so we don't have any free variables, meaning when we don't have free variables, we only have pivot variables and we have one solution. So we have unique solutions. So all of these ideas are interplaying with each other. It'll make more sense as you do more examples. So just take these definitions with a grain of salt and then it'll make more sense as we go. All right, let's do some examples. So the first thing we're going to do is how to solve for the reduced for echelon form. So you'll be given a matrix and they'll be asked, what's the reduced for echelon form? Or you'll have to do a problem where you need the reduced for echelon form. You're going to have to do this process a lot in this class. So same thing with matrix multiplication, feel comfortable with it, practice it, do a lot of examples. And again, this is one of those things where it has a lot of steps and you want to maximize the amount of points you get because you could make an algebraic mistake, which I would say happens even more with reduced echelon form than with matrix multiplication. So you want to write out the steps that you're taking in case you do make an error, that the person that's grading like your quiz or your exam or whatever, they can see that you knew the right steps, you just made an algebraic error, and that's what kind of perpetuated down to your final solution. So hopefully you'll get like partial credit for knowing what to do, even if you make a small mistake. But if you don't show your work, there's no way to elucidate that you knew what you were talking about. I'm a very big fan of showing your work, but okay. So for this reduced echelon form example, this is a process that I use to find the reduced echelon form. Essentially, you can do however you feel most comfortable. I feel like this works the best for me, but whatever works best for you. So, all right, let's write this matrix. We're gonna have to write it a lot of times. So 5, 3, 4, 10, 12, -4, 5, -9, 12, 15, 9, 8. Oh, we also haven't talked about augmented systems yet. So this matrix looks kind of weird, right? There's like this weird line in the middle, because this is like a 3 by 3. This is a 3 by 1. I guess together it's kind of like a 4 by 1 or a 4 by 3. It's weird, right? So this is what's called an augmented system. The word is augmented system. What that means is, so back to when we talked about how we represent systems of equations, when we have this ax equals b, the way that we solve it is that we want to solve for x, and the way that we do that is we do a augmented with b is equal to x. These two things tell us the same information, and the way that we do that is, so this is our system. To solve it, I would augment a with b, so 2, 3, -5, -4, line, vertical line, not a bracket, just a vertical line, and then I write 5, 8. So in this form, this is my coefficient matrix A, and then my solution, like B, is on the right hand side. The X is like temporarily gone because that's what we're solving for. So that's what the idea of augmentation is. So in this case, they're asking us to find the reduced echelon form of A augmented with B, which is what you're going to have to do to solve these systems, is what is the solution with A and B? What is the X? That's kind of what this is asking us. All right, so let's do it. Step 1, I always make the top left value equal to 1. So we know we want those leading ones, right? So first thing I'm gonna do is I'm gonna try to make this top left value have that leading 1 in it. So to do that, I'm going to divide the first row by 5. I can't just divide an entry. I can't just divide this 5 here by 5. I need to divide its entire row. So I'm going to say row 1 is equal to 1/5 row 1. So after I do that, the first row becomes 1, 2, 1. And then everything you also do to the augmented vector. So 15 also divided by 5 is 3. Nothing else changed, so 3, 12, -9, 9, 4, -4, 12, 8. I personally recommend when you're doing your operation that you write like everything that's not changing first, and then you like change the values. I feel like that makes the most, then it reduces error. So trying to reduce problems and algebraic mistakes as much as possible. Okay, so now that I made this leading 1, I'm going to get step 2, make values below 1 equal to 0. So the point is that I have this leading 1, and if you recall, the rules for the reduced echelon form is the leading 1 are the only non-zero entries in their respective columns. So I'm looking at my column 1, and I want to make everything below this 1 into a 0. So to do that, I can say row 2 is equal to row 2 minus 3 row 1. Row 3 is equal to row 3 minus 4 row 1. If you can see what I'm doing here, let me make this color. So I know I'm trying to eliminate a 3 and a 4. So here, how can I make this 3 turn into a 0? I can only use the values around it because everything goes by its column. So like, for example, like I can only do row operations, so the things in their corresponding spots in the rows. To make this 3 into a 0, I can subtract using this 1 up here. 3 times that 1, that gives me 0. So I'm going to use this 1, and then same thing for 4. So 4 times this 1 also will give me the 0 that I want. So I figure out what operation I need to do to make those specific values into zeros, and then I'll have to do the entire thing to the entire row. So, and again, like I said, I always like to keep the thing that's staying the same and write that first. So the first row is not changing. I'm not doing any operations to the first row. So I'm going to do that. My second row, row 2 is equal to row 2 minus 3 times row 1. I know this is going to be a 0. Then I've got 12 minus 3 times 2. 12 minus 6 is 6. 6. If you need to take the time to physically write out what happens to every entry, I recommend you do that because, again, making mistakes in these suck. And you don't even, when you're doing Common Quiz, you don't know if you made a mistake. You don't know what you're expecting. So trying to be as meticulous as possible is going to benefit you so much, even if it feels like it takes a little bit longer. All right, next value. Negative 3 minus 3 times 1, negative 12. Then I've got 9 minus 3 times 3, so 9 minus 9 is 0. Now I'm going to do my third row. So I know that this is a 0, and then negative 4 minus 4 times 2 is negative 12 as well. 12 minus 4 times 1 is 8. And then I've got 8 minus 4 times 3, negative 4. All right, so I've got some zeros, I've got some ones, I'm in good shape. Ideally, I want to make this look like an identity matrix. So the identity matrix, again, remember, is all of those ones along the diagonal and then zeros everywhere else. So I'm trying to do that. When you go about this, not every reduced rational form is the identity, because when it is the identity, there's unique solutions. And like we said, we can have unique solutions, or we can have no solutions, or we can have infinitely many. So it's not always going to end up being the identity matrix, but operating like you're trying to get to the identity matrix is going to help you get to the reduced echelon form. So following those steps is going to be helpful. So the next thing I want to do, this is step 3. Yeah. Make, I'm just going to say calling this matrix A3, 2 equal to 0. So I'm talking about this spot right here. I want to make that into 0. Just because in the identity matrix, I like to think about for these problems, it's like a snake. So you snake down this matrix. So we're starting here, we eliminate these, we go around here, we turn this into a 0, ideally, we turn this into a 1, ideally, and then we go back up throughout the rows and we deal with these values and these values. So that's kind of what my logic is for these problems. So here I can make A3, 2 into a 0. So to do that, I'm going to do row 3 is equal to row 3. So I can use either row. I'm going to use row 2 instead of row 1, because if I go row 3 plus 2, row 2, right? So I have this negative 12. I want it to be equal to 0. If I do plus 2 times 6, so the 6 from here, that's going to make me get a 0. I could technically use row 1 as well, right? So I could say negative 12 plus 6 times 2 is equal to 0, right? This 2 could be used in the same way. However, remember that you're doing row operations. You're not doing entry operations. So whatever you do here, you're going to have to do through. So if I were to do that, this value would go to a 0, but think about what happened to this spot. It would be 0 plus 6 times 1, and that would be 6. We would be undoing the work we've made to make that into a 0. So The point of this is once you make something a 0, you don't want to like make it non-zero again. Excluding the b. Whatever happens with b doesn't really matter. It does not affect what the reduced rational form of a is, which determines the system. So here, I want to turn this into 0, and I'm going to use row 2 to do that. So what doesn't change? Row 1 and row 2 doesn't change. So I'm going to write those down. 3, 0, 6, negative 12, 0. All right. Row 3 is equal to row 3 plus 2 times row 2. The 0 stays as 0. Negative 12 plus 2 times 6 is 0. 8 plus 2 times negative 12, so 8 minus 24 is negative 16. And then I've got negative 4 plus 2 times 0, so just it stays negative 4. All right, so we're making progress. We're getting closer. We're making zeros. We're trying to get to something. So the next thing I want to do, I'm going to take this, bring our matrix down with us, is I want to step 4, make a 3, 3 equal to 1, right? So we're trying to approximate the identity matrix. So we want this value to be 1. To do that, I can just say row 3 is equal to 1 over negative 16, row 3. So I'm going to divide by negative 1 over 16, which is going to make negative 16 1. So again, row 1 and row 2 don't change. I'm going to write those down first. So now row 3 is just dividing by negative 16. So 0 and 0 stay the same. Negative 16 times negative 1 over 16 is 1. And then negative 4 times negative 1 over 16, 1/4. There can be fractions in these matrices. You're going to see fractions in these matrices. Fractions or decimals, dealer's choice. Okay, great. I'm looking great. I have this 1. So looking at this is probably going to be a leading 1 for me. We can see that it's not the only non-zero entry in its row, so we're obviously not even close to reduced rational form, but we're getting there. We're getting somewhere. Speaking of it not being the only non-zero entry in its column, let's make a step towards that. Let's say step 5, make a 2, 3 equal to 0. So I want to make this guy go to 0 because I want this leading 1 to be a pivot variable. For it to be a pivot variable, it has to be the only non-zero entry in its column. So let's do row 2 is equal to row 2 plus 12, row 3. Does that make sense that this, like, we can use this 1 below it to make it go to 0? So we're just figuring out what we need to multiply. Like, what does this value need to be for this 1 to make it go to 0? So in this case, it's just 12. All right. So row 2 is changing, so I'm going to write row 1 and row 3 first. 1, 2, 1, 3, 0, 0, 1, 1/4. Row 2 is equal to row 2 plus 12, row 3. These two things aren't going to change because the corresponding terms in row 3 are 0. Negative 12 plus 12 times 1 is 0. Then on the B side, 0 plus 12 times 1/4 is equal to 3. Great. We're doing great. We're making some zeros, getting closer. The next thing I want to do is I want to make this into a 1. I want this to be a leading 1 in a row, and I want to make everything else around it look good. So this next step, I'm going to make, I didn't write this out, step 6, make a 2, 2 equal to 1. So not too bad. Row 2 is just equal to 1/6 row 2. I'm going to divide by 6 so that I make this into a 1. Again, row 1 and row 3 don't change. 1, 2, 1, 0, 0, 1, 1/4. I'm going to divide row 2 by 6, multiply by 1/6. 0, 1, 0, 1/2. Getting so close. So again, looking at this, let me duplicate this first. The things that are remaining, if we want these to be our pivot variables, which is ideal if we're going to have this look like the identity matrix, we need every entry in its column to be equal to 0 besides that value. So that means in this column, here we're good, here we're bad. In this column, here we're good, here we're bad. We also know that so thinking about in each of these columns, so here, if this is this column that we're looking at, why can't this be the pivot variable instead? Like, why can't I make this go to 0? Or, sorry, why can't I make this go to 0 and this be the 1? Because there's only one pivot variable in each row. So this row already has, this guy is automatically the pivot variable because it's the first leading one. You can't have multiple leading ones. Inherently, a pivot variable must be the leading one. So I know once this row got its pivot variable, this can no longer be a pivot variable. This can no longer be a pivot variable. So we got to go to the next row. Because remember, these rows or these columns are our variables. So we have to change it. So each column, you only have one pivot variable. Each row, you only have one pivot variable. All right, so we're almost there. The way that we can do this is we want to make this go to 0 and this go to 0. So when you're doing these row operations and you're writing out your row operations, I combined these two into the same step because I was doing things to two separate rows. If you're doing an operation to one row twice, so like in this case, these were two successive operations on the same row, I don't want to combine them because obviously they aren't independent, they're dependent, right? What happens from after I did this to this matrix, it impacted what I did to this matrix. So you always want to separate things when you're doing something to the same row. So here, what step is this? Step 7. Let's start with a 2. So let's get rid of the 2. So A1, 2 equal to 0. The way I can do this is row 1 is equal to row 1 minus 2, row 2. Again, I'm going to use that 1 in the second row. Row 1 is changing. Let's write row 2 and row 3 first. 0, 1, 0. That's wrong. 1 half. 0, 0, 1. 1 fourth. All right. So let's do these operations. Obviously, this 1 isn't going to change because this is a 0. 2 minus 2 times 1, 0. And then I have 1 minus 2 times 0, so this stays a 1. And then I have 3 minus 2 times 1 half, so 3 minus 1 is 2. That's the first thing. Cool. The last thing I'm going to do is get rid of this guy, make this into a 0. So step 8 is make A1, 3 equal to 0. I'm going to use the third row to do this. So row 1 is equal to row 3 minus row 1. Sorry, row 1 is equal to row 1 minus row 3 because I can use this one to get rid of this one. All right. Again, row 1 is changing, row 2 and 3 aren't. Let's write them first. All right. Row 1 minus row 3, 1. 0 minus 0, 0. 1 minus 1, 0. Then I've got 2 minus 1 fourth. That's 8 fourths minus 1 fourth is 7 fourths. And that's our solution. This is the reduced row echelon form of A augmented with B. So, yay, we did it. Woo! This is the reduced row echelon form of A augmented with B. This tells us that for my x, so in this case, the system could have been written by like 5x plus 10y plus 5z is equal to 15. 3x plus 12y minus 9z is equal to 9. 4x minus 4y plus 12z is equal to 8, this tells us remember, each column is a variable, x, y, z. This tells us that x is equal, so 1 times x is equal to 7/4. 1 times y is equal to 1/2. And 1 times z is equal to 1/4. Because if I were to take this system, this matrix, and rewrite it as a system of linear equations, it's 1 times x plus 0 times y plus 0 times z is equal to 7/4. The point of the reduced row echelon form is to break it down as much as possible just to get to the gist of it. So in this case, it has a unique solution. It has one solution. There's only one combination of x, y's, and z's that makes this system true. We knew this was going to be a unique solution because the reduced row echelon form of A, so just A by itself, don't even think about the B, was the identity matrix. So if the reduced row echelon form of any matrix, any square matrix, equals the identity. So the identity matrix, again, is where we have those ones along the diagonal and zeros everywhere else. We have unique solutions. Recalling what else we discussed, we had all of those were pivot variables because there was a leading one, which were the only non-zero entry in their respective column. So pivot variable, pivot variable, pivot variable, x, y, z. We know that all of them are pivot variables. We didn't have any free variables, which led us to having unique solutions. And the rank of this matrix is 3 because the reduced row echelon form has 3 non-zero rows. 1, 2, 3. That was a lot to discuss for one problem, but that's how we solve for the reduced row echelon form of a matrix. Now, this one was a unique solution. Let's talk about finding a solution set Ax equals b where it's not a unique solution. Looking at this matrix, I can tell that it's not a unique solution because we don't have a one-to-one correspondence between pivot variables and their solutions. We have free variables. In this case, I'll write it on this one. Our variables are x1, x2, x3, x4, x5. Again, x, y, z versus x1 through x5 does not matter. These names don't really matter. My pivot variables are this guy, this x1, and x4. These are pivot variables because they have those leading ones. They have this leading one and this leading one. It is the first entry in their respective rows, and then within their respective column, everything else is a 0. This is the reduced row echelon form. Looking at that and all those properties, we see this is the reduced row echelon form of this system. Then we have our free variables. So x2, x3, and x5 are our free variables. So we have 2 pivot variables and 3 free variables. And then we have our b. Again, the b doesn't tell us anything about the amount of variables. So this question is asking us to find the set of solutions. So this one case, we have infinitely many solutions because we don't have 0 and we don't have 1. We know we don't have 0 solutions because the only case where we have 0 solutions is if it can't work, right? So in this case, it can work. There's going to be some relationship between x1 through x5 that makes this true. We know that it can't work if we had something like this. So this would be like if that tells us that 0 is equal to 5. That is no solution. There's no way to make that true. When we do the reduced row echelon form, when we do these row operations, it will bring that property out about a system. So like sometimes if there's no solution, it's not very obvious at first. But in this case, when you do those row operations on these matrices, it'll show us a row like this. Like, oh, obviously that can't be true. There's no solution. Okay, so the way that we write these solutions for infinitely many solutions is so first step, sorry, I'm just yapping at this point. We want to write right, the equations that are given to us from the reduced row echelon form. So in this case, I'm just going to go row by row because each row is an equation, each column is the variable. So row 1, the first row, the equation that's given to us is x1 plus 2x2 plus 3x3 plus 4x5 is equal to 0. And then row 2 tells us that x4 plus 5x5 is equal to 6. Everything else are just zeros. So these are the equations that are given to us by the reduced row echelon form. Step 2 is set pivots equal to freeze. So we want the pivot variables to be by themselves. So remember, our pivot variables are x1 and x4. So I'm going to say x1 is equal to negative 2x2 minus negative 3x3 minus negative 4x5. And then x4 is equal to 6 minus negative 5x5. So I've got the pivots by themselves and everything else is set on the right-hand side. The step 3 is set up solution set skeleton is my recommendation. So we want to see what is it going to look like when we solve this. So we know we need to define every variable, like what's happening with every variable in this solution. So it's going to be a column vector, so x1, x2, x3, x4, x5. And it's going to be set equal to stuff. So there's going to be a column vector for every free variable. So I'm going to do this. Every free variable, remember our free variables are x2, x3, and x5. So x2, x3, and x5. There's going to be a column for every single free variable. We need to add another column because the solution is non-homogeneous, so it's not set equal to 0. But no, it's not set equal to 0 because of this 6. If all of these were zeros, we'd be solving the homogeneous solution, which, remember, homogeneous solution, null space, kernel. Those things all mean the same thing. Homogeneous, kernel, null space. But we're not solving that because there's a 6. There's the 6 that makes it not equal to 0. So whenever you're solving for not the homogeneous solution, the non-homogeneous solution, we also need to add, I'll make it a different color, a column for that. There's no variable associated with that because it's just a scalar, it's just a number. So we set up our solution set skeleton. Step 4, I'm going to do within this because I already wrote this out. Step 4, plug in equations. So now all we have to do is put everything about the system into this skeleton. That's why I really recommend writing the skeleton beforehand, because then you can just plug and chug and be done. So x1, let's start with these. So x1 and x4 have actual equations to plug in. So let's do x1 first. So x1, use that color. x1, so looking at the row of x1. Oh, I totally did not know. Whatever, it's fine. x1, there's no number. There's no just scalar. So this is going to be a 0. This is going to be negative 2, negative 3, negative 4. So for everything, so for the coefficient for x2 is negative 2. The coefficient for x3 is negative 3. The coefficient for x5 is negative 4. And that's what I'm going to put in row-wise. Get rid of that box so it doesn't look as crooked. Then I'm going to do x4. x4, so my second to the bottom row, x4 is equal to 6 minus 5x to the x5. This is where this is going to have a 6. That's why we needed this entire column was for this 6. So 6, there's no correspondence with x2, there's no correspondence with x3, and then it's negative 5, x5. That's it. Finally, for the free variables, so x2, x3, and x5, they are just equal to themselves. So in this case, x2 is equal to itself. It only corresponds to x2. x3 is only equal to x3, so I'm just gonna put a 1 in the x3 column. x5 is only equal to x5, so I'm gonna put a 1 there. That's it. That is the entirety of how you solve for the solution set for a system. This is your answer. This is what you would write. Practicing this, I feel like it's also very important because a question is going to be kind of a combination of these two. You have to solve for the reduced or echelon form, and then you have to form its solution. When it's a unique solution like this, it's easier. When it's not, when it's infinitely many solutions like this, where we have free variables, you have to do these steps. So just practice. I feel like it's the best thing you can do. Okay, one more sample, and then we'll do the worksheets. So this is kind of coming at the idea of no solutions, one solution, infinitely many solutions. So we have this system of linear equations. X plus y plus z is equal to b1, 2x plus y plus z is equal to b2, 3x plus 2y plus 2z is equal to b3. This question is basically asking us, what are the conditions for b1, b2, b3? So the what's that equal to, where we have no solutions, infinitely many solutions, and a unique solution. So remember, those are our three options. We want to figure out how does the b1, b2, b3 determine if we have each of those. So to do that, we want to find the reduced or echelon form. So I'm going to turn this into a matrix system. So this becomes 1, 1, 1, where we have the variables x, y, z, 2, 1, 1, 3, 2, 2 is equal to b1, b2, b3. To solve this, I'm going to augment it. So 1, 1, 1, 2, 1, 1, 3, 2, 2, augmented with b1, b2, b3. Let's do this again. Solving for the reduced or echelon form. So first thing I'm going to do, like I said, is I have this leading 1 in the top left-hand corner, so I'm good on that. I want to get zeros below it. So row 2 is equal to row 2 minus 2, row 1. Row 3 is equal to row 3 minus 3, row 1. So what's not changing? Row 1, let me keep that the same. B1. Row 2 is row 2 minus 2 times row 1. This is going to be 0. This is going to be -1, -1, and then it becomes b2 minus 2 times b1. So b2 minus 2 times b1. They're variables, so write out the whole thing. Row 3 is equal to row 3 minus 3 times row 1, so 0, -1, -1, b3 minus 3 times b1. Cool, I'm cooking with gas here. I want to make the second row, I think, I want to have that leading 1 in there because I can see, okay, so looking at this tells me that just from here, this A, row 2 and row 3 are multiples of each other. Like they both represent the same thing, even with the thing on the right-hand side being different. The fact that in just A, so ignoring B, the fact that they are multiples of each other means I'm going to eliminate one of them entirely. So I can't just make all this go to 0. Like I can't just be like, okay, this doesn't matter because this is important. So because I know they're multiples, I know that my reduced or echelon form isn't going to have a rank of 3. It's going to have a rank of 2 or less because this whole row is going to go away. But I can't just make it go to 0 yet. So I'm going to deal with row 2 kind of thing. So I'm going to do row 2 is equal to negative row 2 because I want to get that leading 1 in the second row in the second column. So first row doesn't change. Last row doesn't change. My second row, I'm just negating it. So 0, 1, 1. Negative b2 plus 2b1. Cool. Did not mean to do that. Okay, now that I've done that, next thing I want to do is I want to get rid of my row 3 because I can now use those leading 1s to get rid of some stuff. So row 3 is equal to row 3 plus row 2. Doing that is going to make negative 1s both go to 0. So row 1 and row 2 don't change, so I'm going to write those first. B1, 0, 1, 1. Negative B2 plus 2B1. That's really bad. So row 3 is equal to row 3 plus row 2, 0, negative 1 plus 1, 0, negative 1 plus 1, 0. B3 minus 3, B1 minus B2 plus 2B1. So this, I can take this, and this simplifies to B3, negative 3B1 plus 2B1 is negative B1, negative B2. I just rewrote this. The last things I need to do to make this into an entirely reduced or echelon form is I want to have those leading ones where they need to go, and I want, for those pivot variables, they need to be by themselves. So in this case, this is a pivot variable and this is a pivot variable. So that means that this must go away. This must be a 0 at least. So I'm going to do row 1 is equal to row 1 minus row 2, because that's going to get rid of that 1. So row 2 and row 3 don't change. 0, 1, 1. B2 plus 2B1. 0, 0, 0. B3 minus B1 minus B2. So this makes, then row 1 is row 1 minus row 2. So 1, 0, 0. Because that also gets rid of this 1, which makes this B1 minus B2. Oh, sorry. B1 plus B2 minus 2B1. Which, if I fix that one up real quick, B1 plus B2 minus 2B1 is B2 minus B1, essentially. Okay, looking at this matrix, looking at A, I can see this is the reduced or echelon form because pivot variable, non-zero in its column. Pivot variable, non-zero in its column. That's it. There's nothing here, so this can't be the third pivot variable. So this is our reduced row echelon form. Okay, now that we solved for the reduced row echelon form, it's asking us, are there any conditions on, I'm just gonna write actually this, because we're gonna need it for the other questions too. Is there a case where this system can have no solutions? So there's no way for it to be true. Remember, something has no solutions when it has a 0 row in A with a non-zero value in B. So in this case, I have my 0 row in A. For if this is non-zero, it has no solutions. So B3 minus B1 minus B2 not being equal to 0, that makes it no solutions. That's it. All you have to say. You show the reduced echelon form and you say, if this value is not equal to 0, we're going to have no solutions. Similarly, are there any conditions B1, B2, B3 that will result in having infinitely many solutions? So looking at this matrix, we know we have infinitely many solutions when we have a free variable and we don't have 0 solutions, right? So free variable makes it not unique, and having not 0 solutions must mean it's infinitely many. So we will have these infinitely many solutions if this is equal to 0. So if B3 minus B1 minus B2 is equal to 0, that means that we would have 1, 0, 0, B2 minus B1, 0, 1, 1, negative B2 plus 2B1, 0, 0, 0, 0. It doesn't really matter for our intents and purposes here how this infiltrates the rest of like these two values, because all that matters is that they would form a system that would have infinitely many solutions. So this is the condition where we'd have infinitely many. Are there any conditions, B1, B2, B3, that would result in the system having unique solution? Unique solutions arise when we have no free variables, when we only have pivot variables. There is nothing we can do to B, so B to any of these values, that changes the fact that we have a free variable. Like, no matter what, we will still have this x3 being a free variable, or I guess it's z in this case. There's no way for us to change that z as a free variable. So the answer is no. No case with unique solutions. So the gist of this question kind of is that B determines no solutions versus infinitely many, but the matrix, the coefficient matrix itself, A, determines if there is unique solutions or not. That was a lot of talking, and we just have a few worksheet questions to get through, and then we'll be done with 2.1. Okay, so in this problem, we're just practicing multiplication. So part A is, so we have this matrix A, a 3x3 matrix A with columns A1, A2, A3, and then we have a column vector C where we have lambda, mu, and I always forget what that one's called, nu. Write the result of the matrix multiplication AC as a linear combination of the column vectors AC. So this is just asking us, what does it mean to compute AC when we have column vectors within A times some scalars. So looking at this, we know it's defined because this is a 3x3, it's a 3x1, these match, so the result is going to be a 3x1 as well. It's always row times column. So in this case, the first row is going to be the first row is just going to be what the product is. So it is this value times the column A. So we can't write it like this row, and this row as we've been doing previously, but we can represent it as lambda times A1 plus mu times A2 plus nu times A3. This question is kind of getting you to question different ways of representing matrix multiplication. We're going to need to do this type of multiplication later, so that's why it's kind of asking you to do that. Then they're saying, okay, what if we have a matrix with rows, R1, R2, R3, and we multiply R by A? So R is a row matrix, R1, R2, R3, times A, which is a column matrix, A1, A2, A3. Again, 3x3, 3x3. We're going to have a 3x3. In this case, it's the dot product of each row times each column, because that's what essentially we're doing. We always do is we do the row dotted with the column. So first row, the row times the column, row times the column, rows times the column. So in this case, it's row 1 dot A1, row 1 dot A2, and so on and so forth. So row 1 dot A3, row 2 dot A1, row 2 dot A2, row 2 dot A3, row 3 dot A1, row 3 dot A2, row 3 dot A3. The idea of a dot product will come back in week 7, so keep on the back of your mind. I would assume you guys know what a dot product is. Okay, last question for 2.1 is worksheet questions. So consider the following system of linear equations. It's just asking us kind of to solve it as we did for the solving that we did earlier. So let V be the set of solutions x, y, z. Find a 3x3 matrix A and a 3 vector B so that the above system can be written as AV is equal to B. So again, it's just finding the coefficient matrix and the B matrix. So that's just going to be 2, -1, 2, 1, -3, 1, 1, -2, 1. This is my A times my V, which is x, y, z, is equal to B, which is -5, 5, 2. Write the augmented matrix system and perform Gaussian elimination on it. So they want us to solve this. 2, 1, 1, -5, 5, 2. So finding this allows us to find the reduced echelon form, which gives us the solution set. I'm going to give you the reduced echelon form for now, but you should practice this on your own. So 0, 1, 0, 1, 0, 0, -4, -3, 0. So this becomes the reduced row echelon form of A augmented with B. What is the rank of A? And then what is the rank of A augmented with B? So the rank of A is 2, right? There's 2 non-zero rows, there's 2 pivot variables. The rank of A augmented with B is also 2. If the rank of A augmented with B is greater than the rank of A, we have no solutions, because that would mean that there's zeros in rank in the matrix A, there's a non-zero value in B. So that kind of talks about what we did earlier. They want us to describe the kernel of A, meaning they want us to solve for the kernel of A, which is the null space, which is the homogeneous solution. So to do this, we would take the reduced row echelon form, which was 1, 0, 1, 0, 1, 0, 0, 0, 1, and instead of setting it equal to -4, -3, 0, we set it equal to 0, 0, 0. We're solving for the homogeneous solution. What is it when it's set equal to 0? We've got x, y, z. X plus z is equal to 0, and y is just equal to 0. I'm going to form my skeleton, x, y, z. I'm not going to have a non-homogeneous column vector here because it's homogeneous, right? So all I do is I have a column vector for my free variable, which in this case is z. So z is going to go right here. And then I'm going to plug in the information provided. So x is equal to -z. So this is my pivot variable being terms of the free variables, and then y, which is my other pivot variable, is just equal to 0. So x is equal to -z, so x is equal to -z, y is always equal to 0, and then z is just equal to itself. So this is the kernel of A. How many solutions does the system have? Why, if it does, find all of them. So like we just talked about, back to this question they're talking about, not the kernel. How many solutions does the system have? Our options are infinitely many, unique, or 0. We know it's not 0 because we don't have a 0, 0, 0 with a non-zero row. There's no row that's true, and we must have something like this for this to be 0 solutions. We know it's not unique because we have a free variable. Therefore, we have infinitely many solutions. Whatever it is, find all of them if it has solutions. So we have infinitely many, so we're going to do the same thing we did in part D, but now we have this as our solution set. So first thing, what equations do we have from this? So x plus z is equal to -4, and then y is equal to -3. We form my skeleton, x, y, z. We still only have our free variable z, but we also have this non-homogeneous vector. This becomes x is equal to -4 minus z, and this is still y is equal to -3. So plugging these in, x is equal to -4 minus 1z, y is equal to just -3, and then z is only equal to itself. So this is the solution. Note that this was the solution to ax equals b, right? This was the solution to ax equals 0. The solution to ax equals b will always contain the solution to ax equals 0. It'll just have something else. So the solution to ax equals b will always contain the kernel. It'll always contain the null space. It'll always contain the homogeneous solution. Keep that in the back of your mind. So this was 2.1. It's a lot of content, and it's a lot of, I think, new operations that you're gonna have to get used to doing. So practice, practice, practice. I feel like I'm gonna say that every time in these videos, but just it really helps to do these practice exercises that when you encounter them on a quiz or on a question that you're unfamiliar with, you have an idea of where to start and what to do. But yeah, okay, that's 2.1. Good luck with your studying.